All right, chemists, we'll get started now. Right before we get started, though, I'll just announce and remind you all that online homework grades are live, so any partial work you do in online homework will populate the Carmen gradebook until the due date, and then that's when penalties start to be applied. So I made an announcement earlier in the week, but I'll just reiterate that I found an issue with one of the homework questions in Chapter 7, so I gave everyone credit for it. And so that probably already auto-populated the gradebook, and so you might see a 1 out of 60, but don't worry about it, okay? As you do more questions, it will improve that grade. I gave you free points. Don't complain about it, all right? So you do have more time. Chapter 17 is not going to be due until way after spring break, so you have time to earn those points. All right, so we're going to continue on with Chapter 17 and talk about all the weird ways we can use K and inspect chemical equilibria. So we left off talking about buffers. In Chapter 16, we looked at calculating the pH of just an acid using its Ka. We looked at calculating the pH of just a weak base using its Kb. Chapter 17, we're looking at buffers, in which a buffer contains both the acid and its conjugate base in large quantities. So the idea here is if we take the negative log of the Ka expression, we get the Henderson-Hasselbalch equation, where the concentration of base and acid are in large quantities. This is different than the small amount of, conjugate base you make in a Ka expression. No, we're deliberately putting in acid and its conjugate base, or base and its conjugate acid, in large quantities. So these are in the units of molarity, concentration, but as long as both the acid and the base are in the same volume, we can also look at mole amounts. And so this is where we left off, calculating buffers using the Henderson-Hasselbalch equation for Chapter 17. But the thing is on midterm 3, we'll give you a lot of different examples, like calculate the pH of this system. First, you need to identify, is the system that's given a buffer? Then you use the Henderson-Hasselbalch equation. But if it's not a buffer, then you don't use this equation. So that's definitely a learning objective in this chapter, is what is in my beaker? What expression, what equation do I use to calculate pH? That's the big idea and the thing we'll work on moving forward. So these are specifically buffer questions. So the idea is we have acid and its base directly in the beaker. And that is a buffer. That's how we get our base to acid ratio here. So let's look at this first one. Let's calculate the pH of a buffer that is made by mixing 0.15 moles of HF and 0.5 moles of sodium hydroxide. All of this is in 1 liter. So we see, yes, this is in fact a buffer. We have HF, that is our acid, and there is NaF, F minus, that's its conjugate base, so that is the base. So we have base and acid for our Henderson-Hasselbalch equation. So the piece of information we're missing is pKa, though I give you Ka. So based upon what we know about the P function, what is pKa? Negative log of that Ka value. So this is just a constant, all right, that we're just kind of representing Ka in a different way. We're just going to take the negative log of it and see that this is equal to 3.18. All right, and so this pKa is specific to the substance that we're studying. So this case, it's a HF buffer system, or an HF system. So at this point, we can just plug in our numbers. Recognize that we need our HF concentration. This is our acid. So the concentration, if we convert this into molarity, is 0.15 moles of HF over 1 liter. So we see that this concentration is 0.15 molarity HF. We have to do the same thing with F minus. So this is the base that goes into our Henderson-Hasselbalch. And we see that, with the numbers given, half a mole of NaF or F minus in 1 liter is equal to 0.50. F minus. So these are my base and acid numbers that I put into the Henderson-Hasselbalch. So pH equals 3.18 plus log base over acid. So what number goes up top? 0.5 or 0.15? Which number? It's 0.5. We want to put the base, so F minus concentration. So 0.5 molarity of F minus the base over 0.15 molarity, or yeah, 15 molarity, that is HF on the bottom. And you see we get a pH of 3.7, right? So I did the work of converting to molarities because I want to prove to you. Yes, the Henderson-Hasselbalch equation says, okay, molarity base over acid, but would we have still gotten the same answer if we would have just left those amounts in moles? Yeah, because we divide by volume, the same volume in both the numerator and denominator. So it's fine for us to stay in the unit of moles of base over moles of acid. I'm trying to show you tips and tricks to speed up calculations for exams and for practice and online homework and such. You can stay in the unit of moles, right? So I could have just put those mole amounts, 0.5 over 0.15, and still gotten the same answer. All right. So let's do a different one here where it's still an HF system, but this time we're mixing together the acid and the base components. So this is a good example where using millimole is really important and can save you some time because dividing by 1,000 and working with little numbers is really annoying. And since we're just getting the base to acid ratio, it is fine to stay in a millimole amount. So let's calculate the pH of a buffer made by mixing some HF and some NaF. So here's the thing. If you multiply a molarity by a milliliter, you get a millimole. Okay, just multiply those numbers straight up. So 25 times 1, that's 25. So there is 25 millimoles of HF present in this mixture. Okay. I like that number. I don't want to divide that number by 1,000 if I don't have to. So just stay in millimoles, because as long as we get a millimole of sodium fluoride and divide them, the ratio is still going to be the same. 12 times 1, that's simple enough. I can do that in my head, is 12 millimoles of F minus. I like 25 and 12. I don't like 0.025 and 0.012. Those are annoying numbers. All right, so millimoles are really useful here, because all we need is the ratio. Here are our numbers for our Henderson-Hasselbalch. So pH equals the same pKa as before, so 3.18 plus log base over acid. What number is going to go up top, 12 or 25? 12, yep, that's the base. And then HF is the acid. So this is just 12 millimoles of F minus over 25 millimoles of HF. Again, no, it's not necessary to divide both those numbers by 1,000. All right, and so what we get is that the pH is a little bit more acidic, and that makes sense because there's more acid, the acid component present. So this is a pH of 2.86. It's all about getting the base to acid ratio. You can be in molarity, you can be in moles. So let's look at a different system. We did an acid, Ka. Let's look at a base buffer system. We still use the same Henderson-Hasselbalch equation. It's just identifying what is the base, what is the acid. So here we are mixing ammonia and ammonium chloride. So of these two things, which one is the base? Ammonia or ammonium? Ammonia is the base, yes. So our convention's still the same here. Ammonia is the base, so NH4 plus ammonium, that is the acid. Perfect. And so these are just concentrations. So those are the numbers that go straight into Henderson-Hasselbalch. We have base concentration, we have acid concentration. I don't have pKa. So we can calculate it, but do I give you Ka? Nope, I give you Kb. So if I take the negative log of this number, what value am I calculating, actually? pKb, yeah, so pKb for this, did I write this down? I did not. Negative log of, oh no, I already know what it is. 4.74, that's pKb, all right? How can we get Ka, though? Kw, yep, just like before. So Ka is Kw over Kb. Again, we're assuming this is 25 degrees. So Ka is equal to 1e negative 14 divided by 1.8 e negative 5. 5.55 times 10 to the negative 10. So that's Ka. And so if I take the negative log of that number, we get pKa is equal to 9.26, right? So Ka and Kb, they are related by Kw. pKa and pKb, how are they related? By, is there anything special about those two numbers? They add up to 14, yes. They add up to 14. And the reason they add up to 14 is because pKw, so negative log of Kw is 14. So that's how you can convert between pKa and pKb is via 14, just like pH and pOH. All right, because we actually want the 9.26 number. That's the number that's going into our Henderson-Hasselbalch equation. We always put in pKa. Ammonia has you look up its pKb, so we have to convert it to calculate pH. But once you get pKa, it's simply enough, 2.96 plus log, what number goes up top? The 15.15 molarity, that's ammonia, the base, and then 12 goes on the bottom, that's NH4+. All right, and so yes, we get our pH down there, 9.35. Okay, all right, let's do one more. Let's calculate the pH of the mixture when we mix these things. So it looks like we're mixing unequal amounts of ammonia, so 200 milliliters of ammonia, and 800, I'll just write it, 800 milliliters of ammonium, all right? So do we want to put our base to acid ratio in molarity, or should we choose a different unit? Millimoles, yeah, let's do millimoles. So hopefully you get on board the millimole train. It's very nice and easy. Easier, so 200 times 0.4, I think that is 80 millimoles of base is present, so this is ammonia. And then 800 times 0.1, oh, that's also 80 millimoles of ammonium, NH4+, that is the acid form in our Henderson-Hasselbalch. So there we go, there we got our base to acid ratio. So simply pH is the same pKa we got before, so 9.26 plus log 80 over 80. 80 over 80 is 1. What is the log of 1? 0, yes. And so we see pH is equal to 9.26. So we see pH equals pKa. And so this is a special case. pH equals, is equal to pKa when you have the same amount of acid and base in your buffer, all right? So if you have equal amounts, you have like 1 mole and 1 mole of the other one, all right? Your pH is equal to your pKa based upon the identity of your system. So that's kind of like a special occasion that happens with pH when it's those two amounts are equal. Yes? We do, yeah, and you could, so you can make a Henderson-Hasselbalch for POH if you wanted to. It's in the textbook, but it's not necessary to memorize 2 equations because it's easy enough to convert between pKa and pKb. And usually we reference solutions in terms of their pH. Like if I tell you that a solution has a POH of 8, like that's just annoying if I told you that. It's better if I just tell you the pH, all right? Yes, there is another one, you could derive it yourself or look at the book. Okay, so let's do 2 more. But this time we're going to use the Henderson-Hasselbalch differently because in the last 4 examples, we just figured out how much base and acid we have, we plug and chug. So how else can we use the Henderson-Hasselbalch? Well, I can give you different variables. I can give you pH. Like in this question, I'm telling you what the pH is of this buffer. And we can solve for the base to acid ratio. So it looks like I have pH, I can figure out what pKa is, and so I am solving for what that base to acid ratio is. So here is the given pH. Here's Ka, so you can calculate that pKa for acetic acid is 4.74. I promise you by midterm 3, you will memorize the pKa of acetic acid is 4.94 because you will use it so many times. All right, so we're going to plug these numbers into Henderson-Hasselbalch and just solve for that missing ratio piece. So pH equals pKa plus log base over acid. That's what I'm solving for. So 4.70 equals 4.74 plus log base over acid. So I'm solving for that fraction in the logarithm. But actually, before we answer the question, if the pKa is 4.74, but the measured pH is 4.7, what do you think is more present, the acid form or the base form? Acid, yeah, because the pH, the actual measured pH is a little bit lower. So we should expect that more acid is present in the buffer. So let's see if we're right. So subtract some stuff, and you get that negative 0.04 equals log base over acid. To undo a logarithm, we do 10 to the negative 0.04 on both sides. And so what we get is that the base to acid ratio equals 0.912. All right, so the question is, well, what does that mean? Since this is the ratio, this number represents a ratio, right? Base over acid, representing it as a fraction will help you understand what this means. Base to acid ratio means there is 0.0912 units of base for every 1 unit of acid. That's what it means. So I just put that number over 1 to recognize, okay, for every 1 of the denominator, acid, there has to be 0.912 units of that base to make this buffer. So which one is more present, the acid or the base? The acid, and so we were right. Good. All right, so that's the ratio. So let's use that ratio to figure out how much acetic acid we need to add to sodium acetate to make this exact buffer. So when I do this, I think, what is this, 250 millimoles of sodium acetate. This is 250 millimoles of which component, the base or the acid? If I say sodium acetate, that is the base, yes. So that's the number I'm going to start with, and I'm going to convert using this equality I just got to get how much acid I need, because this is the ratio I need to make this buffer. So I'm going to start with 250 millimoles of base. I'm going to use this equality or use this ratio, but I'm not going to I'm going to think about it. Do I multiply by 0.91 or do I divide by 0.91? Divide, yeah, so I'm already in the unit of base, so I want to put this base number in the denominator. So 0.912 units of base is required for every 1 unit of acid. And so the unit's millimole, whatever. And so, yeah, we get that we need a little bit more acid present to make this buffer. So 0.274 millimoles, 274 millimoles of acid, but then convert that into moles, 0.274 moles of acid. Perfect. And so then if you divide base over acid with these amounts, you should get 0.912, right? So in these examples, we're just working with the Henderson-Hasselbalch a little bit differently. I give you a pH. With that pH and given pKa, you can get what the required base to acid ratio you need to achieve that pH. Okay, so in all of these examples, I've essentially given you straight what is the base, what is the acid, and how much of each you put into the solution. So to make a buffer, that's all you need. You just need acid and its conjugate base, or base and its conjugate acid. You need those two things in the solution. So in all the previous examples, I've just given you how the mole amount or the molarity of each of these, you plug it into the Henderson-Hasselbalch and you're good to go. But there's another way you can make a buffer, and this one's a little bit more complicated because it requires a BCA table. but you achieve the same thing in the end. You achieve having acid and conjugate base present in very large quantities. We've already done 6 examples of the first way to make a buffer. I just tell you how much acetic acid and sodium acetate you have, and you plug B over A, that's it. The second way to make a buffer is start with your acid, so acetic acid, and then you add strong base, like sodium hydroxide. When you add a strong base, you neutralize some of your weak acid to make its conjugate base. And that's another way you can make a buffer, right? Again, all we need is both the acid and its conjugate base present in large quantities. So that's what this second kind of thing is saying. The next part is we're going to look at examples where we partially neutralize something with a strong acid or base. If we start with HF, add sodium hydroxide, we will make NaF its conjugate base in that container. And those two amounts allows us to use the Henderson-Hasselbalch equation. It's just a little bit more complicated because we have to do a BCA table first. All right, so I'll show you what I mean. All right, this is the second way we can make a buffer. Be very careful of what substances I'm showing you here. Here, we're mixing 80 milliliters of HF and 15 milliliters of sodium hydroxide. So what do you want to do? I'm working moles or millimoles? Millimoles. So how many millimoles of HF? 8 millimoles of HF. And then how many millimoles of this second thing? 3 millimoles of sodium hydroxide. So do not just look at those substances and say, oh, that's 8 units of acid, there is 3 units of base. We can't do that because in the Henderson-Hasselbalch equation, base over acid, it's not any base, it's not any acid, it's a acid and its conjugate base. Here I have HF, is sodium hydroxide its conjugate base? No, so we cannot put 8 and 3 in the Henderson-Hasselbalch. We have to figure out how much conjugate base we make via this neutralization. So the first thing we need to do is use these numbers, neutralize the system first, figure out how much acid and conjugate base I have, then do your ICE table. Basically just put those numbers in the afterline in your Henderson-Hasselbalch. So here's the neutralization reaction first. I'm taking HF, it's an acid. I'm taking the base, sodium hydroxide. Acids and bases react. Do the double displacement reaction, and you see, look, one of your products is NaF. It is the conjugate base, and HF is your acid. And the other thing is water, but that doesn't affect our pH. Yeah? We are not doing an ICE table yet, because we're doing a neutralization reaction first, because this is an acid, this is a weak acid, and this is a strong base. This is, oh, okay, this should be BCA, sorry. Yeah, okay, sorry, it's a BCA table. I didn't write any numbers yet, so it wasn't a nice table. Okay, so this is a BCA table. So the idea is I'm neutralizing this. So I put my numbers down that we just got earlier from the millimole amounts. So there is 8 millimoles of HF, and there is 3 millimoles of sodium hydroxide. So let's recall BCA tables. They need to be in the unit of moles, or millimoles, whatever. ICE tables, they're in the unit of molarity. So with BCA tables, it's not about, okay, which way does the reaction shift? No, this reaction always moves in the forward direction, but we need to identify what is our limiting reactant. I hope with easy numbers you can see what is obviously our limiting reactant, which substance? NaOH. So limiting reactants get fully consumed, so minus 3 millimoles of sodium hydroxide. If I consume 3 millimoles of sodium hydroxide, what else is consumed? HF, but how much? Minus 3. So it's minus 3, but then what's produced on the other side? Plus 3, right? So notice that ICE tables and BCA tables, they're vastly different. ICE tables, they only move, forward or back an X amount. But with BCA tables, they move completely in the forward direction. So we see after this neutralization reaction, we have 5 millimoles of HF. We have no sodium hydroxide left. And then we have 3 millimoles of NaF. And then we have 3 millimoles of water, but who cares about that? All right, it's not affecting our pH. So look at this afterline and tell me, what's in my beaker? You have HF and you have NaF. What is that? That's a buffer. And how do we calculate pHs of buffers? With the Henderson-Hasselbalch. So these are the two numbers that you put into your base to acid ratio. That's it. We're taking this afterline. We're going to do we're going to make all of the approximations in the ice table and then just go ahead and use the Henderson-Hasselbalch equation, all right? pH equals pKa log base over acid, right? Remember, the Henderson-Hasselbalch equation is the ice table with all of the approximations already made. All right, so pH, pKa, what was pKa for HF? I think it was 3.18. We got that before. So pH equals 3.18 plus log, what number goes up top? 3. 3 millimoles of F minus is present in this mixture, and only 5 millimoles of HF, and then that is our pH. Notice, it's 5 millimoles of acid, 3 millimoles of base, not the 8 and 3 that we had initially. This 3 millimoles was millimoles of sodium hydroxide. We need to figure out how much sodium fluoride, the base, is present for the Henderson-Hasselbalch, right? That's what makes this one a little bit different, partial neutralization, different than the other kind of easier ones that we were doing earlier. Okay, let's do another one, this time with a base. So we are mixing 8 millimoles of ammonia, so NH3, and what is this other thing? This is HCl, so 3 millimoles of HCl. So I have a weak base and a strong acid. This is the second way we can make a buffer, via partial neutralization. So I didn't give you ammonia and ammonium straight up. You have to figure out how much ammonium is there by neutralizing it first. So here is the BCA table, but this time between the weak base ammonia and HCl, so the reaction's a little bit different. But what you see here is that adding HCl makes the conjugate acid that we need for the Henderson-Hasselbalch equation. So we just need to put the appropriate numbers in, right? Limiting reactant is HCl. So I consume all of that, so then I have no more HCl left. I have to consume 3 millimoles of ammonia, but then I gain 3 millimoles of that ammonium. And so we see after this neutralization reaction, we have 5 millimoles of ammonia and 3 millimoles of ammonium, and then water. If those two things are in my beaker, what is that? That's a buffer. Yes, so if that's a buffer, can we use the Henderson-Hasselbalch? Yes, we can. All right, so we're gonna do pH equals pKa. What was pKa? Okay, pKb is 4.74, and so pKa is equal to 9.26, I think, for ammonia. Right, and so pH equals 9.26 plus log base over acid. What number goes up top? 5. Ammonia goes up top, ammonium goes on bottom. So see again, it's 5 over 3. It's not 8 over 3, it's 5 over 3. A reaction is happening to make that ammonium. And then there we go. There we get our buffer. pH is 9.48. Right? So we just, in these examples, have to do a tiny BCA table to figure out that base to acid ratio for Henderson-Hasselbalch. But hopefully after you do enough of these, like mixing a weak base and a strong acid, you'll realize a trend and kind of a pattern, and then maybe you don't actually have to write the full BCA table. You can predict how that neutralization will work because it's always a 1-to-1 ratio for everything, right? So I urge you, like, do the BCA table like 10 times, and then you'll see the pattern emerge. Okay, ooh, one last tough one. All right, and then a demo? No, one more slide, then the demo. Okay, so let's prepare a buffer between HF and sodium fluoride. What is the pH of this buffer? Can I just put those numbers Straight into the Henderson-Hasselbalch. Are you sure? What's in your solution? You have HF. What is that? An acid. And then you put in NaF. What is that? It's conjugate base. You can put those numbers straight into the Henderson-Hasselbalch. All right? These are the questions you need to be asking yourself. So pH is simply pKa, so 3.18, plus log, what number goes up top? 0.2, yep, and then over 0.1. And again, since these are given in molarities, you can convert them to millimole, but you don't have to. Since they're both in the same volume, we can keep them there. So this is F minus on top, and then HF on the bottom, base over acid. So we see that the pH is, what is it, 3.481. That's the pH of this buffer. Okay. Now, let's take this buffer and add 10 milliliters of HCl to it. Before we even solve it, which way should the pH go? Up or down? Down, because we add acid, it should become more acidic. But now let's prove it and showcase how a buffer resists pH change. Because you would imagine if we add acid, like, because HCl is a strong acid, right? It should drastically change the pH. If it was pure water, right, it would become really acidic. But with buffers, we'll see that the pH only changes minimally. And the reason is because this added acid goes into reacting with one of the things in this buffer. HCl is an acid. So which one of the components of the buffer will that acid react with? NaF, the base. So let's write the BCA table for that. We have NaF, it reacts with HCl to give me HF. So what I'm doing is just doing like the double displacement reaction. So HF is one of my products, so it's my other product, NaCl. Perfect. All right, so we'll do the BCA table. Right, what is the unit in a BCA table? Moles. So here, everything's in molarity, so I need to convert all of those into moles. Do you want to work in moles or millimoles? Millimoles, yes. So 100 milliliters of 0.1 molarity HF. How many millimoles is that? 10. 10 millimoles of HF is present in this mixture. And then I think there's 20 millimoles of NaF present in this mixture. Right? So those two values go in our before line. I have 20 millimoles of NaF and 10 millimoles of HF. Okay, I know I have things on two sides, just trust me for now, okay? That's what we're starting with. Now we add acid. We add strong acid, so how many millimoles is this? 2. There is 2 millimoles of HCl we're adding, so I'm gonna put a 2 under HCl. Okay, just think about the forward reaction. What's my limiting reactant? HCl. So in the change line, it's going to be what? We're going to consume all that HCl, but then I also have to consume 2 of the base, but then I add 2, of the HF. Do I get anything else? 2 NaCl. So we started with 0. We also gained 2 NaCl. So after this neutralization reaction, notice it's not an equilibrium, it is fully reacting. I have 18 millimoles of NaF. I have 0 HCl. I have 12 millimoles of HF, and then I have 2 millimoles of NaCl. All of this is in my beaker. How would you calculate the pH? We have NaF, we have HF, and we have NaCl. Can we ignore one of them? Which one can we ignore? NaCl. Why? It's pH neutral, yes. So we can just focus on the other things, which are acids and bases. So what's left? What does this create? NaF and HF. What is that? That's a buffer. So if it's a buffer, what equation do we use? Henderson-Hasselbalch. Can I just do 18 over 12 then? Yes, I do. Yeah, that's it. That I have literally 18 millimoles of NaF and 12 moles of the acid HF. Those two numbers go straight into the Henderson-Hasselbalch equation. We already did the neutralization. So this is pH equals 3.18 plus log Base over acid. So there is 18 millimoles of F minus, 12 millimoles of HF. All right, and that is the new pH. And so we see that pH is now 3.356. So did the pH go down? Yes, it did when we added a little bit of acid. So the reason, but did it change that much? Nope, just changed it a little bit. And here's the reason. All of that H plus just goes to changing this base to acid ratio. Look at this line. Before we did the reaction, the base to acid ratio was 20/10. Then we added 2 milliliters of acid, and I literally just took some of the base, millimoles of the base, and made it 2 millimoles of the acid form. So I'm just changing this ratio when I add HCl. I'm not drastically changing the H plus concentration nor the pH. I'm just changing that ratio. And that's how a buffer works. So if you do add a strong acid or a strong base, to our bodies or whatever, our pH doesn't change drastically. And the reason is because all we're doing is changing the base to acid ratio, and we see pH does not really change that drastically with a buffer. All right, and that's what I basically say on this side. When you add strong acid or strong base, all you're doing is changing the ratio of base to acid, so your pH doesn't change that much. This is also called the common ion effect, and that's how buffers resist pH changes. Mathematically, your pH is equal to your pKa when base concentration equals acid concentration. That's also the best region on your titration curve. It's when your solution is the most buffered, when base equals acid. Because when you add a little bit of strong base, that number won't change as drastically, that ratio, mathematically, right? So some ideas about a buffer, these are the concepts. Again, contains both large amounts of HA and A minus at the same time. You deliberately have both of them present in large concentrations. That resists pH changes because of adding strong acid or strong base changes that base to acid ratio. And then here are some other ideas. Your buffer is most resistant to pH changes when you have large numbers in your base to acid ratio. When you have a lot of moles of stuff to neutralize, that's high concentrations are more resistant to pH changes, because adding acid or adding a strong base will only change the numbers in that base to acid ratio a little bit if the numbers already start off big. And so in general, what we see here is a titration curve, but this solution is really only buffered well, meaning that adding base in this example minimally changes the pH, just kind of in this range, but volumes outside this range. So kind of like at the beginning of the titration and towards the end of the titration, we see the pH changes a lot drastically with added base. And so in those regions, we don't have an optimum buffer. We still use the Henderson-Hasselbalch equation, but in general, the best ratio for a buffer is between 1 and 10 for your base to acid ratio. So between either a 10 to 1 or 1 to 10 ratio. That's what we're looking for. If I have like 1 unit of acid and 20 units of base, that's kind of outside the optimal buffer region, right? So those are some ideas about how buffers resist pH changes, and it's all due to this BCA table, right? The ratio will change minimally if the before values are very large, but your base acid ratio will change a lot if these concentrations, these mole amounts, are very small numbers. So let's do that demo, and I will show that to you. All right, so I got some stuff here, some solutions. Did I bring my goggles? Yes. All right, I got some solutions. I got water and acid, and then 2 buffers. 2 buffers. So they are all kind of the same color-ish. But here I have 2 buffers. Here I have just plain water. Is this water a buffer? No. Do you think this water will resist pH changes? No. So I have HCl. So what will happen when I add HCl to this water? It'll become really acidic. Do you think the color will change? Probably, because it's not resisting that pH change. It's literally going to get all of its protons, H plus, from this acid. I'm literally going to add 1 drop. 1 drop, and we'll see what happens. 1 drop. Okay, that was 2 drops, but oops. Okay, did that change? Heck yeah. All right, so that is acidic now. So I'm going to put this to the side. All right, that's HCl. That's acidic. We'll see how can we make these solutions acidic. This is a 0.1 molarity buffer, so that acid and conjugate base are 0.1 molarity, and this is a 1 molarity buffer. So which one do you think is more resistant to pH changes? 1 molarity or 0.1 molarity? 1 molarity. There's more moles of junk here to react with my strong acid. So remember, I only put 1 drop of strong acid in here. So let's see what happens when I add 1 drop to each of these. All right, so 1 drop. Do we think that the pH will change a lot? So that was 1 drop there. There was, oh, I did 2 drops by accident. Okay, so did that change color? Not really, not like crazy like this one did. Did that one change color? No. All right, so for both of these, I'm going to give it a squeeze. So we obviously saw that 1 drop did very little to the pH. So let me give it a nice squeeze. There's 1 squeeze, 1 squeeze. Okay, is the pH starting to change in this one? Yeah, it's starting to change. But what about this one? No. All right, so let's see how much this one needs. So I'll give it 2 more squeezes of acid. Is it starting to change? No? Yeah. It's not changing? There we go. I gave it a 1 long big squeeze. Is it changing now? Yeah, barely. All right, so now this one's finally changing its pH, but I had to add a lot of acid to do that strong acid. Because there's so many moles of stuff for it to neutralize, you're changing the base to acid ratio only, versus pure water, not resistant to pH changes at all. At least a buffer like this, even a weak one, is able to resist pH change a little bit because you're just neutralizing the weak acid, weak base system in your Henderson-Hasselbalch equation before pH really, really changes. Yes? So the question is that why drinking a full 1 liter soda will kill you? I don't think it's the acid that will kill you, like your crazy change in pH. There's probably other factors like all of that gas. I don't know, is there data to back it up? If you drink a full 2 liter of soda, you will die? Is that a challenge? I mean, I feel like if I was given money, I'd try to drink a 2 liter. I don't think I'd die. Maybe, I could be wrong, but I don't think so. The thing is that soda is it's a weak acid, right? Like phosphoric acid, carbonic acid, those are all weak acids. I was adding strong acid here, so if you die, I don't think it's due to pH changes. Okay, all right, so there's buffers. Okay. All right, so with buffers, it's base to acid ratio, right? But you have to be looking for your weak acid and its conjugate base, or base and conjugate acid. So a mixture of a strong acid and strong base is never a buffer because there's nothing to put in the base to acid ratio. So we have to calculate pH a little bit differently in this example, but it's not that bad. We still do a BCA table because a neutralization reaction is happening between this HCl and this sodium hydroxide. We just calculate the pH a little bit differently, but you already know how to do this, right? So I'm mixing HCl and sodium hydroxide. So I want to work in millimoles because I'm lazy. So I have 4 millimoles of HCl. And then how many millimoles do I have here? 10? Is that 10? Someone, yes, is that 10? Of sodium hydroxide? Okay, all right, 10 of sodium hydroxide. So these 2 numbers go in my before line, but these are 2 strong acids, strong bases. But we still do the same concept. Acids neutralize bases. So I have 4 millimoles of HCl, 10 millimoles of sodium hydroxide. What's my limiting reactant? HCl. So minus 4, but then it's plus 4 plus 4. Okay, so after this reaction, I have 0 moles of HCl. I have 6 millimoles of sodium hydroxide. And I have 4 millimoles of NaCl, and then I have water. Okay, if this is in my beaker, how do I calculate the pH? I have both of those things. Can I ignore one? Can I ignore one of them? Yeah, which one? NaCl. That one because it's pH 7. I can't ignore sodium hydroxide, but you can tell me, is this solution going to be acidic or basic? Basic, because hydroxide is in excess. Do we remember how to calculate the pH of just sodium hydroxide? Negative log, but it's negative log of what? 6? No, we have to figure out what the concentration of this sodium hydroxide is. Then we negative log it because it's just a strong base. We don't even have to do an ice table here because all that's in our beaker afterwards is a strong base and a salt that we can ignore. So the concentration of sodium hydroxide is 6 millimoles over its total volume. What is the total volume? 90. Yeah, so 90 milliliters. Remember, a millimole divided by a milliliter is a molarity. So never did we have to convert to liters, which is very nice. And so you get that after neutralization, that sodium hydroxide concentration, 0.066. You can calculate POH as something. It's probably, I think I can do that in my head, 1.28 or something like that, and then subtract from 14, you get a pH of 12.8. Right? So here, between a strong acid, strong base, honestly, the calculation's easier. It's just a BCA table. Take the excess thing. That's what dictates your pH. Never did we have to do an ice table. Because is there anything weak here? Nope, everything's strong. But you still have to do that BCA table to figure out what's in excess. Okay. Before I move on, what do you think the pH of a strong, at the neutralization point? When you do a titration, if you have a equivalence point of your strong acid, strong base, what do you think the pH is? 7, and it is 7, but let me prove it to you. So I'm going to erase these numbers, all right? Pretend you do a titration and you add 10 moles of HCl and 10 moles of sodium hydroxide. What's my change line going to look like, left to right? Minus 10, minus 10, plus 10, plus 10. So after this neutralization, at your equivalence point, like when you're doing your titration, right? You have 0 HCl. You have 0 sodium hydroxide. But then you have 10 millimoles of NaCl, and then you have water. What is the pH of that? 7, because the only thing in your water is what? NaCl, which is a neutral salt. All right, so that's why if you look here at these titrations, between a strong acid and strong base only is pH 7 at the equivalence point. If you look very closely here, okay, that S dot is where your equivalence point is, not the inflection point, but where your graph basically is vertical. Those pHs are 7. That's when your moles of acid equal moles of base. All right, so strong acid, strong base, never a buffer. You guys want to play a game? Okay. I told you there are 2 ways to make a buffer. So you tell me, when you mix these 2 things, is it possible these things can mix to make a buffer? Remember, there are 2 ways to make a buffer. The goal is you need HA and A minus in that solution. Just somehow either add them directly or via partial neutralization. All right? Or it can be base and its conjugate acid. That's the goal. So think to yourself, can the 2 things I mix make an acid and its conjugate base together? So let's look at the first one. HF and sodium hydroxide. Is that a buffer? It is a buffer. What kind of buffer? The first one or the second one? It's the second one, yes, where HF adding sodium hydroxide makes F minus in the beaker. There is the HF F minus for your Henderson-Hasselbalch. If I gave you amounts of those 2 things, would you have to do a BCA table? Yes. So number 2, you have to BCA, then Henderson-Hasselbalch. The first one, if I just give you 2 amounts of the acid and base, you just Henderson-Hasselbalch right away. So this first one, you do BCA, then Henderson-Hasselbalch. This is the hardest part of the chapter, is being able to identify via the question, is it a buffer or not? Do I have to BCA, or can I just plug everything into an equation? That's probably the hardest part. So what if I mix HF and HCl? Is that a buffer? No. How do you know? Those are 2 acids. Oh, you guys are so confident and smart. Yes, that's 2 acids. If I put those into solution, how do you think you would calculate the pH? HCl. Yeah, because HCl is the strong acid and HF is a weak acid, so you would just ignore HF. But that one is not a buffer. All right, HF and KF. Is that a buffer? Yes, what kind? The first one or the second one? First one. So you just have to Henderson-Hasselbalch right away. No neutralization. All right, ammonia and nitric acid. Is that a buffer? It is a buffer because we have a base, and what are we adding to it? A strong acid, so that is how we make its conjugate, NH4+, and so that is a buffer. It's a type 2 buffer where you BCA, then you Henderson-Hasselbalch, because a neutralization happens first. All right, next one. Oh, that one's the same, sorry. Okay, next one, ammonia and ammonium bromide. Is that a buffer? Yes, it is. What kind of buffer? The first one. So you just Henderson-Hasselbalch, plug and chug, and you're done. All right. Okay, now with words. Benzoic acid and sodium benzoate. Is that a buffer? That is a buffer, yes. So benzoic acid, that's HA. Sodium benzoate, that is NaA. So do you have to BCA this? No, you don't. You just Henderson-Hasselbalch right away. I like your confidence, though. So that's a buffer type 1. There's no strong things. There's no neutralization happen. You just put that straight in the Henderson-Hasselbalch. All right. Benzoic acid and KOH. Is that a buffer? Yes, it is. Because adding KOH to benzoic acid makes sodium benzoate. So do you have to BCA this one? Yes, you do. BCA, then Henderson-Hasselbalch. That's a type 2. Do you like this game? All right, benzoic acid and HCl. Why is that not a buffer? 2 acids. Yes, it's 2 acids. So that one's not a buffer. All right, let's keep going. NaCN and HCN. Is that a buffer? Yes, that is NaA, and there is HA. That one you just Henderson-Hasselbalch right away. Good, okay. Sodium hydroxide and HCN. Is that a buffer? Yes, it is. Here is HA, that's your weak acid. Adding sodium hydroxide will give you A-. And so yes, this is a buffer. You have to BCA first to figure out how much A- you make, then you Henderson-Hasselbalch. Okay, HCl and sodium hydroxide. No, it is not a buffer. Yes, it's an acid and a base, but it's a strong acid and strong base. So that's not a buffer, but you can still calculate the pH. Just BCA, take whatever's left over, you just pH it like directly. No ice table needed. All right, NaCl and HCl. Huh? It is not a buffer. No, it's not a buffer. Because NaCl is pH neutral, it's 7, and HCl. So this mixture is just acid. That's it. You just pH it and go. All right, so that is not a buffer. Yeah, so basically take your HCl concentration and then that you just get your pH directly. All right. And it's because chloride is not a weak base at all. It's a charge neutral or a pH neutral salt. Okay, sodium hydroxide, and that is acetic acid. Is that a buffer? Yes, it is. It is a buffer where we have to BCA first and then Henderson-Hasselbalch. So here's acetic acid. Just squint your eyes. It looks just like HA or HF, whatever, because it has to be a weak acid. So if we add sodium hydroxide, a strong base, that is how we make A-. in the beaker? Oh yeah, here are the hard ones. Yeah, okay. Is that a buffer, the next one? It is a buffer, because if you squint your eyes, what does that look like? NH3, it looks like NH3 if you squint your eyes. This is essentially NH3, where I replaced one of the H's with a CH3. And that would make this NH4 plus. So this is a buffer. Do you have to BCA? No, you Henderson-Hasselbalch right away. Okay, next one. That thing and sodium hydroxide, is it a buffer? No, it's not, because it is 2 bases. Yes, it's 2 bases. That is your weak base, and then you're adding sodium hydroxide? Like, no. All right, next one. That and that. Yes, that is a buffer, because now you have a weak base and you're adding a strong acid. So you have to BCA first, then you Henderson-Hasselbalch. Do we like the game yet? Kind of. All right, nitric acid and KOH. It is not a buffer, yes, because those are 2 strong things. You can still calculate the pH, right? You can just still do a BCA table, figure out what's left over, calculate the pH. All right, and the last one. Is it a buffer? It is a buffer, yes. Because this is essentially NH3, where I replaced all of the H's with just CH3s instead. And then this one is essentially NH4 plus. But again, all the H's are replaced with a methyl group. So this one, do you have to BCA table this? Nope, just Henderson-Hasselbalch right away. All right, that's the game. We'll do another one later in the slide. Okay, so here's the thing. You know how to calculate the pH at every single region on this titration curve. Every single one we've done already. You just need to figure out which calculation to use. And that previous slide was supposed to help you identify, okay, am I looking at a buffer or not? Because I know for a fact you're going to, for this next exam, you're going to try to Henderson-Hasselbalch everything. But you don't do that, because you only Henderson-Hasselbalch when it's a buffer. And what did we see? Only like less than half of these were actually buffers. They're just mixtures of things. We have different strategies on how to calculate pHs. So this part of the chapter, part 3, basically just reintroduces all of the concentrations and calculations we've already learned, but just in a different context, in a titration. So we're using all the same things. We just need to think at these different portions of our titration curve as we add sodium hydroxide to a weak acid. What is the thing in my beaker? That's what you need to be asking yourself all the time. What's in my beaker? How did I learn how to calculate the pH of that thing? So let's talk about it. Let the titrations begin. What is in your flask? So how a titration works, at least this one, we're going to start with a weak acid. And then we're going to slowly add strong base. You'll do this in lab, and you'll add, with your burette, add a little bit of base, and you'll measure the pH. But the thing is if you know how much base you add, you could calculate what the pH, the new pH would be. As long as you know the concentrations and the volumes of everything, you can calculate it. And that's what we're going to do on paper, right? So the idea here is, okay, here's your start of your titration. Here is your equivalence point. Right there is where that maximum slope is. That's when your moles of acid is equal to your moles of base. There are different things present in all of these different pHs. So let's think about what is present in your beaker at the very beginning of your titration. Pretend you put 10 millimoles of HA into your beaker and you have 0 sodium hydroxide. So what I mean by my beaker is in your Erlenmeyer. In your Erlenmeyer flask, you start with HA, that's it, and then you slowly start adding sodium hydroxide. So before your titration begins, this is what's in your beaker, or your Erlenmeyer. So what is present in that Erlenmeyer when you measure the pH? The only thing that's present. Acid. A weak acid. Do you know how to calculate the pH of a weak acid? Yes, Yes, I like that confidence. So that was from chapter 16, right? You know, if I gave you HA and I gave you Ka and its initial concentration, you can calculate pH, right? So at volume 0, HA is the only thing that is present. So all you have to do is x squared over initial concentration equals Ka. That's it. That's how you calculate pH. You know how to do that, right? Yeah. Right, and that's how you get pH. All right. What if we add 2 milliliters of sodium hydroxide? So let me just make up some numbers. What if I have 2 millimoles of sodium hydroxide, 10 millimoles of HA? If I mix those the two things together, what kind of solution do I get? A buffer, because you lose some of the HA, but you gain some of the NaA. And so if you have HA and NaA present, then you have a buffer. How do you calculate the pH of a buffer? Henderson-Hasselbalch, yes. But you have to BCA first to figure out where you are on that titration curve. All right, what if we are at 8 milliliters of sodium hydroxide? So 8 milliliters. So -8, -8, +8. Have we reached our equivalence point yet? No, we haven't. So this is still a buffer. This is still a buffer. So we use the Henderson-Hasselbalch. So we're like right here. We were like here, now we're there. But now what at 10 milliliters? That is our equivalence point. So here at this point, we've converted all of the HA to NaA. So let me change these numbers. So at the equivalence point, I now have 10 millimoles of both of those. So after these things react, what? I'm going to have 0 of that, 0 of sodium hydroxide, 10 millimoles of sodium A-. So if this is in my beaker, do you know how to calculate the pH of NaA? Yes. NaA is a what? It's not a neutral. If HA is a weak acid, A- is a base, So how do you calculate the pH of NaA, a weak base? You have to use Kb. So at your equivalence point, when you titrate a weak acid, at your equivalence point, we don't have NaCl. You actually have NaA, which is a weak base. Do you know how to calculate the pH of a weak base? You do x squared over initial concentration, but it's equal to Kb. But that is equal to Kw over Ka, right? So the difference here is when you're titrating a strong acid, strong base, at your equivalence point, you have NaCl, which is a neutral salt. But if you titrate a weak acid, at the equivalence point, you have a weak base. So you actually have to do an ice table. Okay, pretend that we add 12 milliliters of base. So now, what is my limiting reactant? It's actually the acid. So if I do -10, +10, let's think about what's at my, after this reaction. I actually have 0 HA, 2 sodium hydroxide, and 10 sodium, my weak base. So if I have these two things in my beaker, how do I calculate the pH? Yeah, OH-. So sodium A, so our weak base gives some hydroxide, but a lot? No, it's a weak base, but sodium hydroxide's a strong base. Does one of them take over here? Yeah, it's just going to be the sodium hydroxide. So at 12 milliliters, you have NaA and hydroxide, but we're going to assume that it's just the hydroxide that dictates the pOH. And that is how we interpret a titration curve. You technically know how to do all of these calculations already. It's just when do you use which one? But being able to notice where your equivalence point is, if you know where your equivalence point is, you can tell, okay, before the equivalence point, you're in your buffer region. You need the Henderson-Hasselbalch. At the beginning of your titration, you just have acid, so it's just x squared over initial concentration equals Ka. After the equivalence point, it's excess space. And those are calculations you already know how to do. So let's do it. Okay. Before you begin the titration, so we've added 0 milliliters of base so far. We have 10 milliliters of acetic acid. The only thing in my acid is HA. You know how to calculate the pH of this, but I will just remind you. All right, so ice tables should be in the unit of molarity. So 0.1 molarity of HA, nothing of the other stuff. This reaction has to go forward. The HA only, that's the only thing in there. Plus X, then we have 0.1 minus X, X. Equilibrium line goes into Ka. I tell you for acetic acid, Ka is 1.8 times 10 to the negative 5. So that equals x squared over 0.1 minus x. Can you solve that? Yeah, but do you want to do the quadratic? No. So let's just get rid of that minus x. And so we see x squared, or x, once you make that approximation, is 1.8 e negative 5 times 0.1 square root. X is 0.00134 molarity, but molarity of what? H plus. Why is it H plus? Used Ka. Also because that's what I defined it. X is H plus concentration. Right? And so then, yeah, you just negative log that and get the pH. pH equals 2.87. You put acid in your Erlenmeyer, it should be acidic. 2.87 is acidic. Great. Now, let's add base. So how should my pH change? Should go up. So it better go up. So now we still have that 10 milliliters of weak acid in your Erlenmeyer, but now the only difference is you add 2 milliliters of strong base. So we need to figure out how those two things react. Acids and bases react with one another, so we have to do a BCA table first before we can figure out what pH calculation to do. So we have the same amount of acid, but now we have 2 milliliters of base. So let's get millimole amounts. So this looks like 1 millimole of HA, acid, and then this is 0.2 millimoles of strong base, sodium hydroxide. Acids react with bases. So I want to neutralize that weak acid with that strong base. So when I write out my BCA table, I start with 1 millimole of HA, 0.2 millimoles of hydroxide. My limiting reactant completely reacts. So if I completely react that hydroxide, I have to consume some of my HA, but what else happens? I make some A minus. I also make water, but I don't care about water. So after this neutralization reaction, I have 0.8 millimoles of HA, and I have 0.2 millimoles of A minus. If both of those things are in my beaker, what is it? That is a buffer. Yes, that is a buffer. So can I just put those numbers straight in the Henderson-Hasselbalch? Yes, you can. Perfect. Yeah, so the next step is do the ice table. But remember, the Henderson-Hasselbalch equation is your ice table with the approximations already made. So we're just going to put these into your base to acid ratio. So pH is equal to pKa, so 4.74. Plus log, what number goes on top? 0.2 moles of your acetate over 0.8 millimoles of your acetic acid. All right, and so we see HA and A minus are present. That is a buffer. So use the Henderson-Hasselbalch. Your pH is 4.14. Did the pH go up from the previous question? Yes, it did. Good, because we added base. All right, so that's adding 2 milliliters of sodium hydroxide. So let's add 3 more milliliters of sodium hydroxide, so the total volume added is 5. What is the new pH? So our pH should continue to go up, but let's check it. So this is the exact same process, just with different numbers. So we have 1 millimole of acid still, but now we are adding 0.5 millimoles of sodium hydroxide. So the only thing that changes here is that sodium hydroxide in our BCA table. We still started with 1 millimole of HA, but now it's 0.5 for hydroxide. So minus 0.5 plus 0.5, and then because all the hydroxide is reacting. I hope you're seeing the pattern. You're seeing the pattern with the BCA table. And then afterwards we have 0.5 millimoles of HA, and then we have 0.5 millimoles of A minus. What is that? If both of those things are in my beaker, what is it? That's a buffer, yes. Can I put that in my Henderson-Hasselbeck? Yes, you can. So, but can you get the pH right away? Do you know what the pH is? Yeah, what is the pH? It's equal to pKa, because this is the special region where base equals acid concentration. So log of 1 is 0, and so we get that the pH equals pKa here because we have log of 1, all right? So our pH is, 4.74, right? So where this is on our titration curve is right here, the halfway equivalence point, where you've halfway neutralized your acid with base. So you're halfway there. So when you're halfway there, your pH that you measure with your probe is your pKa value for that specific acid. Okay. All right, let's keep going. What is this? We add 10 milliliters of acid, 10 milliliters of base. Do you think this is a buffer? It's probably not. It's probably not. So let's look at it. But let's check to see what is in my beaker by using the BCA table. All right. So we still started with 1 millimole of acid, HA, but now we also have 1 millimole of base, sodium hydroxide. So I'm going to put those numbers in and check what is in my beaker afterwards. One of that, 0, 0. What does my change line look like? -1, plus 1, plus 1. So after this neutralization, I have 0 HA, 0 hydroxide, 1 A minus, so A minus, remember, is a weak base, and then 1, I guess, mole of water. But I've been ignoring water all this time. So all of this is in my beaker. Can you calculate the pH of that? Yeah, what's the one thing that matters here? A minus. A minus is a weak base. So if A minus is present in my buffer, or sorry, in this reaction vessel, I don't actually want to use the Ka expression. I want to use the Kb expression because A minus is a base. But simply, we know with the Kb expression, I just need to do x squared over initial concentration equals Kb. And I can calculate what x is, I can calculate the pH. But remember, initial concentration, is my concentration 1? It is not. So the concentration of A minus is actually 1 millimole over what? What volume is that 1 millimole in? It's not 10 milliliters, it's 20 milliliters, yes, because I'm diluting this entire thing. So we see that the new concentration here is 0.05 molarity A minus. So essentially this question became, what is the pH of a 0.05 molarity weak base solution? But here's Ka. That's what this question became. But you had to know that by doing the BCA table first, right? And recognizing where you are on this titration curve. So where this is on the titration curve is right here. Right at that red point, that is when A minus is present. Where we started right here, we had HA present. In the middle, we have the buffer. All right? So let's actually solve this question. So x squared over 0.05 equals Kb. So Kw over Ka. So 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5. This is chapter 16 stuff. And so we get x is equal to something. 1e negative 14, 1.5, negative 5 times 0.05 square root. I get x is equal to 5.3 times 10 to the negative 6. But that's the concentration of what? OH minus, because we used Kb. And so you get POH and then you get pH. And you do see, in fact, the pH continued to rise. It continued to go up to 8.2. So in all these subsequent steps, our pH is climbing because we're adding base. But the way we calculate it is a little different for each of these. Okay, we did 0 milliliters of base, 2 milliliters of base, 5, 10. What do you think we're going to do next? 12, yeah, or I don't know, what is it? It's actually 11. We're going to go a little bit past the equivalence point. We're going to see how to calculate the pH. I told you, you know how to already do all of these already. So we're going to add additional sodium hydroxide, so we're past the equivalence point. Same strategy. Do a BCA table first to figure out where you are, because we're adding base, strong base to weak acid. We still, not ice, BCA. We still are starting with 1 millimole of acid, but how many millimoles of base, strong base am I adding now? 1.1 millimoles of strong base. So I want to put that in my BCA table. So 1 millimole of HA, 1.1 hydroxide. What's my limiting reactant now? Yeah, Na, HA. So minus what? 1. Minus 1, plus 1, plus 1. So after this reaction has neutralized, I have 0 HA. I have 0.1 millimoles of hydroxide. I have 1 millimole of A minus, and I have water. What is A minus? Weak base. What is hydroxide? Strong base. How do you think you're going to calculate the pH? The strong base. So can we ignore A minus? Yes, we can. We're going to just ignore it because it is a weak base. So we can just ignore it. All right. So with the excess hydroxide, we need to actually get its concentration so we can calculate pOH. So what is this? So hydroxide concentration is equal to 0.1 millimole. That's how much was left over in the afterline. But what is the total volume of the solution? 21 milliliters. Do you like millimoles and milliliters? Yeah, they're nice. You weren't prepared for it in 1210, but in 1220 you're prepared for it. So then what is that? Oh, I already have that there. So the hydroxide in this solution is 0.00476 molarity. Of course, us ignoring this weak base, this is just an approximation. We're making an assumption, but it's fine enough. That strong base is contributing to the pOH fine enough. So that's OH, calculate pOH, get the pH, and you see that the pH is in fact climbing, even more and more so here. All right, so at this point, we are way past the equivalence point. We're in this region where the excess hydroxide is what dictates our pH. So we will stop there. I think that's a good place to stop. Definitely review the 4 different places you can be on a titration curve. These are the 4 equations you'll do. You already know how to do all of them. It's just where are you? And we'll do the weak base example next week.